your sister's Facebook post, and I looked, she got blasted by a motorhome. Somehow there's a jet ski involved. I'm all confused. But I couldn't read the post while I was driving because that'd be dangerous. So I had to wait till I got here. I guess she was dropping a used jet ski off to a guy that was buying it, hit ice, and somehow ended up with a jet ski, and then a motorhome hit her. Anyway, can't make this stuff up. But just because your neighbor's driving fast doesn't mean you should drive fast, right? Some of us Michiganders have been doing this for years, and once we're sideways, we know how to recover. Just saying. Some of us Michiganders, once we're sideways, we don't know how to recover. So you gotta stay away from us. So just because your neighbor's driving fast doesn't mean you should drive fast. I got about 6 things to roll through before I get to the real PowerPoint. The reason we delayed today was because of the roads, but also it's a pretty important lesson if you're actually going to understand antennas. I'm going to phrase it that way. A lot of people don't understand antennas, and you can still pass your tests and stuff, but if you're going to understand how they work, today is pretty important, so we delayed it. I went in and graded a bunch of your labs. Once we're measuring a bonding jumper, and a bunch of you were at like 0.7 milliohms, 0.5, and I'm like, I originally graded it, and you can put some comments in, and I'm like, really? I think you were a digit off, because 0.7 milliohms is like tiny, tiny. And then I went over to the box and measured a couple, and I'm like, what it's measuring? So I manually bumped your grade back up. So if you get a comment about that, just ignore the comment. It's kind of hard to go back and claw those comments back. But as you're measuring them, be thinking about that. Our range is, it's got to be less than 3, less than 2.5 milliohms, right? Move that decimal over to one more spot. We're talking minuscule resistance. So every once in a while, I'll grab like a jumper wire and measure it, and it'll be like 25 milliohms, 28 milliohms. So 0.7 is pretty small, but so if you see a comment on yours, you can kind of ignore it, but do make sure you're measuring it. The static wicks have this question on that lab about, it'll say, is it a flexible / semi-flexible or a null? I'm going to touch on that at the end of today's lecture. I'm not sure what I'm going to do next year yet, which doesn't affect you, but without today's lecture, it wouldn't have made sense even if I explained it to you before. Anyway, so I have not been paying real close attention to if you labeled it flexible, semi-flexible, or null so far, but the very last slide today is going to point that out. So I just mentioned that to say, oh, I'm still working on the labs too and learning some of the words in there that I didn't catch the first time I scanned them. I am holding on to a bunch of your lab 2s where you turn them in. Let's see, lab 2. You're giving me readings, right? What are the readings you're giving me on lab 2? Static wicks? Yeah, static wicks. So when you're measuring milliohms, I'm getting a lot of papers that are coming through the exact same milliohm, which might mean you had 4 or 5 of you measuring at the same time, which I get, but I'm going to hold on to them just to make sure I don't continue to get that same number. If you want that back, let me know, but I don't think there's really anything on there where you would want it back. I was double checking with Dean and some other ones on your mock-up board that you're doing, A or B. Most of them are missing paint on the surface, so it's possible to do it. If you are actually doing this measurement like in an airline or on an actual aircraft, a lot of times they'll have a little bit fancier milliometer that's got almost like 2 sharp needles on it that you can actually like poke it through the paint. I'm going to say scratch the paint, but it's almost more of a poke it through the paint to get the measurement, which brings up the bottom of that lab says to go get a milliohm reading on the 414, right? Well, our milliometer needs an extension cord, and now there's snow out there. So I'm going to say just skip the 414 one. Go ahead and put a comment on there like skipping this year. Later in the year, if you want to grab that out and double check one, I was gonna move some of the static wicks up from the vertical stabilizer, down to one of the wings where they were taken off. Without the fancy pricking device, you would have to scrape the paint off the beach, and we would have paint scraped all over the place on the beach jet. So you're probably not gonna get that on a practical for O's and P's. If you did, you gotta take a little bit of paint off, and or make sure you're following the manual. I don't know that anybody's got it on a practical, for actually checking one of those. But for what it's worth, yeah, you gotta get underneath the paint, if you're actually gonna check it correctly, and there's a special tool for it that we just don't have. Is that making sense for everybody? So on the boards, it should be good enough concept practice, for what we're doing. Oh, I was supposed to pull up one other slide from the last presentation. Who you call if you set off a ELT unsuspectingly? The answer is you can call all the way down to, I say Florida. But, what are the letters they give us again? SARSAT. So it gives you on this one a 1-800 number, U.S. Air Force Rescue Coordination. Basically, if you're familiar with Civil Air Patrol, that's essentially who you're calling. It's the people that dispatch Civil Air Patrol. So you could call them, or if you were to read the whole thing, it actually says you can call your local Air Traffic Control. So I have, for us here, I have Great Lakes Approach saved on my phone because I'm a pilot, and every once in a while, well, I had to land in the dark once with no radios, so I had to call them on the cell phone. So if you're a mechanic in an area, not a bad idea to figure out, hey, who is my local air traffic control, so that if you set off a ELT or one's been going off, you're like, you know what, instead of calling Florida and trying to tell them where I am in Michigan, you could just call your local ATC, Air Traffic Control Center, and say, hey, we've had an ELT going off, just want to let you know it was a mistake, or blah, blah, blah. So, anyway, but found that online to tell you, hey, what do we do? Cool. All right. 414. We're checking the radios out there, and the transmit stopped being strong. And we were like, what's going on? And then all of a sudden we started getting funny fuzz. We were like, what is going on? Well, we drained the battery. The battery went dead on 414. Radios take a tremendous amount of power to transmit, right? So 3 or 4 groups later than 414, basically the battery got low enough that the radios weren't working anymore. So for the ones that were in there, it was actually a pretty good lesson on, when your battery goes dead, you might not realize it because inside the aircraft, the lights were still on, stuff was still happening, but usually the first thing to go, if you're a pilot, if your alternator goes and you don't notice the little light come on, we didn't have the engines running, so didn't notice, right? The first thing to go is your transmits get weak. So when I was coming back, flying at night and lost my alternator, lost my power system, the first thing I noticed was nobody's responding to my calls anymore. And it was 5-10 minutes later that I realized, oh, it's because they can't hear me. And about 5 minutes after that, my lights started to dim a little bit. And I was like, oh, that's what's going on. So radio transmissions out are one of the first things to go. And just kind of be aware of that, especially as we're talking about radio systems and whatnot. Ziegelbauer made it. Did you scan in? Because
I tried to, it just looking on my face, but it wasn't doing it.
that's fine. Terry said you have a grace today. So I was just checking to see, to make sure if I have to undo it. All right, we made it. So that is one of the things to be aware of is the radio transmission out's the first thing to go. Usually you can still hear in. this on yesterday's slideshow, Ziegelbauer. Basically, you're going to call SARSAT, which is essentially who dispatches Civil Air Patrol. Otherwise, they do say, I didn't find it on here, but they do say your local ATC, Air Traffic Control. Now that I said it out loud, I don't see where it says that, but it says it on there. I read it the other day.
Right out your nearest.
It's right here. Or your nearest FAA air traffic facility. So if you're a mechanic somewhere, I recommend saving that. I have it on my phone. Just in case. Okay. Back to 3. Monday, I told you I was coming in. I am still planning on coming in, but I forgot I set up an appointment at 9 a.m. So I probably won't be here till 11. One person grabbed my cell number, but if you're thinking you may or may not come in, do make sure you grab my cell phone and check with me, because you never know what kind of plans I change. I am kind of planning Monday, then the rest of the day, and then Tuesday, but get my cell phone. Don't just show up and assume I was going to be here, because I said I might be. Okay, let's get rolling with the real stuff. Antenna is going to be a fun day. What do antennas communicate with? We already talked a little bit about, well, they communicate with pretty much everything. Your cell phone actually has an antenna in it that uses basically the same technology we're talking about today. It's a little chip, maybe a centimeter long. So it's going to use this very similar technology to what we're talking about. This is showing an aircraft talking with GPS, talking with other aircraft, talking with the ground station. Does anybody remember the letters that we usually use for this? WASP, good job. Wide Area Augmentation System. Basically, we're talking with a whole bunch of stuff. So we got to go back, all the way back, to electrical theory for this. So we've got cases wrapped. I should have reviewed this to make sure I didn't get the words wrong, but you got right, left, right. Curl, curl, shoot, shoot. And you've got, yeah, I'm trying to remember what word it was. It was current, 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 induced, like duck, 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 goose. Really, what we're going to focus on is one of these first ones. When we have a current going through a conductor, it sets up a magnetic field that, if you wanted to visually check it, it's going in a direction. And when we say magnetic field in a direction, usually we draw the lines when we're drawing them. That north to south direction is the way those flux lines are following your fingers. So anytime we have current, there will be a magnetic field that gets established. And we call it an EMF radiation, because we'll talk about it later, but it's both magnetic, and then there's an electrical component to it as well. But if you think about it kind of just as the magnetic, it makes things simpler when you're thinking through, and that's probably all the level you need to get. So we're going to put radiation, EMF radiation, kind of, as Dean would say, cookies on the bottom shelf, which means I'm going to teach you a pretty basic level. It's going to be way more than pretty much anybody else in the world knows. Not in the world, but, you know, people you're going to talk to. And if you want to go deeper than that, you can read the first 30 pages of chapter 11. And it'll go a little bit deeper, but even with that, depending on who's explaining it, it can get a little bit trickier. Now, if I go all the way back to our first electrical, we would talk about holes, talking conventional theory, right? So basically, I'm going to explain everything in conventional theory. It's going to make more sense that way. So all day we think about conventional. So when we say I've got a charge moving, it's not actually the electrons, it's the holes, the reverse. So I'm talking conventional theory. But the other piece of it is, when I got the cups and we lined it up and talked about holes, we only had one molecule, actually one atom, I guess you'd say, wide, going by. The frequencies that we're dealing with antennas are so high that we almost have to go back and think static electricity. Now I hesitate to say that word static electricity because by definition, what is static electricity?
Sitting there.
Just sitting there not moving, right? So it's like, oh, how can you say it's static electricity when it's moving all over? Well, it's kind of, you're back to the idea of, if I was to have a object like that, where is most of the static going to end up at, or the charge build up at? It tends to build up at the points, right? So if I was to draw an object like that, the static will tend to move to the points, and you'll have, if I put them as pluses, you're going to have a lot more pluses there, and there is still a charge, but it's very much heavily loaded towards the point. So you can have where it's more dense in one area of your object than it is in another area of your object. So when we talk electricity, when it's not a crazy high frequency, if we have a wire and a circuit, a battery, normally if we hook this up, I better put a load in there. Normally if we hook this up, and I say, hey, I've got 2 amps coming out of my battery. When we're doing our math, we say, okay, if there's 2 out of the battery and there's 1 amp here, we know I have the other amp coming through this one, right? If I have 1 here, I have to have 1 here, because whatever leaves my battery has to come back in the battery. So that's our basic electricity when we're doing the math on stuff. When we're dealing with radio frequencies and super high frequencies like this, the polarity of my AC generator is moving back and forth so fast that even traveling at the speed of light, if I were to send out a plus pulse, as that plus pulse traveling at the speed of light is moving down this wire, by the time it even gets to the load, my alternator already switched to saying, no, it's a negative pulse. And now I've got a negative pulse kind of coming out, and it just gets kind of wild back and forth. We're going to learn about that, we're going to see it today, but because part of my wire is still working on sending that plus pulse down the wire, while another part of the wire is actually experiencing the negative pulse, because this electricity travels at the speed of light, but I switch plus minus so fast that even before my load gets the plus, I already switched to negative. So because we're switching back and forth so fast, it's not quite so linear as I can say, oh, I got 1 amp here, I got 1 amp there. Because our charges, or if you want to say our electrons, they can get where they're almost like piled up in areas as it's switching back and forth so fast. So that's part of when we're doing this. I want to point that out so that if your brain gets stuck like it should on, well, if I got 1 amp here, I got 1 amp there, you got to kind of go to like a little bit more static electricity where I could have slightly different charges at different spots on my wire because we're switching so fast. And you'll see that today in a couple videos and stuff like that. So, speed of light. I always had the hardest time remembering the speed of light because there was no real reason. It's fast. It's so fast I don't even care, right? It's just crazy fast. Until this lesson, and now I'll never forget it. I'm going to round it to 300 million. So 300 million, because we're so close to it. So I'm not going to get real specific with 29.970, right? But 300 million meters per second. So that's a number that you don't necessarily have to memorize, but in the antenna, in the frequency range, we're going to use it a lot, and it's fairly easy to memorize. So 300 million meters per second is the speed of light. The speed of light in air is slightly slower than in a vacuum. A vacuum would be in space, right, where there's actually not any matter that is traveling through. So matter stuff does slow down the speed of light slightly, but the reality is we're in the thousandths or 10,000ths range. It's fairly insignificant, our atmosphere versus a vacuum. So you can, if we're rounding to 300, you can round to 300. We're not gonna get so crazy as to say, well, are you like at 30,000 feet or are you at sea level? I'm not gonna go that far. If you wanna get really deep on low frequency waves, follow the curvature, and high frequency don't, then you can go there, but we're not gonna get quite that deep. So 300 million, and we're in the neighborhood. I did the math, 0.03% is the difference. Not much difference. Water, on the other hand, just FYI, water very much slows it down. In water, you're only at 226 million. So if you try to send a radio wave through water, it's at a quarter, almost a quarter percent, a 25% reduction as it goes through water. But the other part with water is the effectiveness in water is very minimal because it's magnetic and electric of sort, right? It's an EMF wave, not just an MF wave. Because it's an EMF wave, when the E part interacts with the water does funky stuff, and it basically, for long distances, stops it. You can get a couple meters, maybe a couple feet through water, but radio waves pretty much don't work in water. Now that said, if you slow it down to a slow frequency, the lower the frequency, it'll still work. So there used to be actually what they call Project ELF, extreme low frequency, up in Michigan, up in the UP. It was this antenna that was, I didn't write it down, a crazy long antenna for this low frequency, and they communicate all around the world with our submarines during the Cold War. So it was a low enough frequency that this low frequency could actually go through the water to get to the submarines to communicate with them. But the antenna was it hundreds? Was it hundreds of yards long? If not a mile long? And you'll understand why it had to be so long, but it makes it fairly impractical for the rest of us because we can't carry around a couple 100-yard long antenna with us, right? So you can go through water, but basically not. All right. Just having a field or not doesn't let us pass a whole lot of information quickly. It just says kind of a yes or no. And when I say a field or not, if you didn't have AC power, if we just had DC and we turned it on, theoretically, if you had a sensor, you could sense, oh, Case turned it on way over there. But then I'd have to turn it back off. You'd be like, oh, Case turned it off way back over there. Oh, Case turned it on way over there. Oh, Case turned it off. We theoretically could sense that, but it's fairly difficult. Just, I'm going to call it a slow pulse of on and off. It would get lost often with the other EMF noise that we're constantly being bombarded with. So what we do is we set up a signal on a certain frequency. And that frequency is kind of like a guitar string. So when you hit a guitar string, basically that guitar string would keep going back and forth forever, except there's some air resistance in the wire itself, right? But once you get it set up, once you strum it, it's going to just keep going and keep on making its wave. So back to if we have a balanced circuit, if our capacitive reactance and our inductive reactance is balanced in a parallel circuit. If you guys remember when we did that math, basically because one of the currents is 90% ahead of the voltage and one of them is 90% behind. Let's see, I won't go that far today. Once you set that up and you plung it, that part of the circuit doesn't take any energy to keep that EMF wave out. It's just, so you got an EMF wave established. Now, there's some inefficiencies because are any of our wires or antennas truly zero resistance? No. So any device that's sending out a signal will have to have some sort of power input. to overcome the resistance that's there. But the basic concept behind them is we strum this antenna to make it go pum. And then once it's established, what we're going to do is we're going to take that baseline strum at a certain frequency, pum, and we're going to look at the changes that happen to it. So we're actually not looking at the pum to say, oh, I'm getting a signal per se. We're going to look at how I change it for where my information happens. So I can do that in two different ways. I can do that in AM, which is amplitude modulation, or I can do that in FM, which is frequency modulation. So if you guys have ever listened to a radio, I'm not that old, right? You guys all listen to radios. You guys know what AM station is? We gotta flip the switch over to AM. Yeah, so that's all the difference between AM and FM. AM is we're gonna change how strong we're sending the signal out. But if you notice the strum, pung, so let's say you tune into, what's an AM station? 1200, whatever. I don't know what frequency they're sending that out on, but there's a frequency associated with it. So you tune into that AM station. Basically, they strummed it, and they're going to change now the amplitude of their signal going out. So it's going to be plum. Wait, that's pitch. Anyway, you get the idea. I'll just go so the part we don't care about, but the info we're sending out is actually the up, down, up, down, up, down. That's where we harness the info from, is AM. And we're going to go deeper into that in a slide. The FM one, we actually leave the amplitude the same. So it should be coming through at the same volume, if you will. But we're going to change the frequency. So if I'm sending it out on 102.9 megahertz frequency, and I'm listening to my station on the way to SMAT, the way information in FM gets through is they'll actually change it from 102.9 to 102.925 to 102.91. Anyway, they're changing the frequency ever so slightly. We have it drawn here so you can see it, but the reality is the frequency change is so tiny that you wouldn't be able to see it. I'm going to show that in a slide. Did I see a hand back there? Somebody's just stretching. All right, so that's the difference. You do need to know the difference between AM and FM. Amplitude modulation versus frequency modulation. That's just the same thing, a little different picture. All right, so in FM radio frequencies, or information, we're varying the frequency, and we're going to cover the waves a little bit more later, but these pictures you got to realize are exaggerated huge. So, we are going to, in a typical FM, we're going to change a 108 megahertz frequency. We're only going to change it plus or minus 75 kilohertz. So if you grab your calculator and do the math, difference between megahertz and kilohertz, you end up at, I thought I had a percentage, 0.07% deviation. It's not much change, is it? We're barely changing it. So if I could say, okay, what's the time, which this is on a timeline, right? So if I said, what's the time difference between each of those peaks? Could I draw it on the board where you'd see a 0.07% change? No, there's no way. But that's how sensitive our receivers are, is they'll pick up a 0.07% change in frequency modulation. So we draw it this way so you get the idea, but the reality is we are changing the frequency, just ever so tiny. I think I had in here, so let's say you're listening to 100.5. I think basically 100.5, the modulation, it might get all the way down to 104 point, 100.425. So there is a kind of change there, but it's pretty small. Now, in that's why, if you're listening to FM radio, that's why our stations are spaced, is our FM radio has to have a little bit of space in between each station, because when you're listening to 100.5, you're actually listening to, 100.425 through 100 point, what would that be? 575. 57. So you're truly listening to a small band of frequency in there, but they don't have to tell you that much when you're on your dial. You just tune in 100.5. So frequency modulation changes the frequency by just ever so small amounts. We'll get into that a little bit more later, but that is that's the difference between AM and FM. This one slide with some explanation, then we're going to take a break, so if you have some questions too. So this shows how we're going to pull information out of AM signal, an amplitude modulation signal. Most of what we use in aviation is an AM signal. So our comms, stuff like that, most of what we use is AM. There is some FM. At one point I remembered what it was, but most of what we use is AM. So what we do is we take our signal, it's the same frequency in AM, so I'm not changing the frequency, but I'm turning the volume up and down on how strong I'm sending it out. And if I do that, it's going to turn it up on both my positive and negative, because a guitar string that only went one way would just be weird, right? So, poing, and as we turn the volume up and down, we're going to have kind of a mirrored on both sides. Well, electronically, we're going to take this signal coming into our device, and we're going to say, you know what, let's just forget about the bottom. So, essentially, using diodes, they're like, let's just forget about the bottom side. And basically, they're just going to say, give me the average maximum. So we took our signal, we forgot about the bottom, and they said, you know what, just kind of give me the average max volt. So now my device is left with this line, an average maximum voltage. And then for audio communications, what they'll do is they'll actually say, okay, now let's take this, and I don't know what that line would be. Let's say it's, I gotta make up a number. Let's say it's 2 volts. It's probably much smaller than that, but whatever. Let's just shift the whole thing down, and we'll give it a new 0 voltage reference line. And now that maximum, we could actually plug that voltage into a speaker, and we could get sound coming out of it that you can hear. So that's one way to use AM to change a amplitude signal that's changing. It's still the same, but it's getting louder, quieter, louder, quieter, louder, quieter. And we turn it into a audio signal that's not just louder, quieter, but it's actually carrying our full noise system, different frequencies coming through it. If we wanted to switch to digital, we could take this same thing and we could say, okay, every up is a yes or a 0, and every drop is a 1 or a no. So we could send the same digital signal and say 1, 0, 1, 0, 1, and maybe they drop that one off so it's not so high. Maybe it'd be better to come back up here and say if it makes it up to 2 volts, it's a 1. If it makes it down, it's a 0. But you can get where we hide our information inside that wave. So that's amplitude modulation, and your radio basically goes inside. We're not going to go that deep into how and why, because I don't know, and you don't need to know, unless you want to start working on radios themselves. So everybody following the difference between amplitude, frequency, and how we're going to pull information out of it? Cool. take 7 minutes, make sure we're back at 5:02. Part of this break's not that you're tired, it's the next part, the meat and potatoes of it, as we say. I bet John likes meat and potatoes. Are you a meat and potatoes kind of guy? Yeah.
I looked up that project bill,
Yeah.
84 miles of it, and I just went 2 locations.
Is that what it?
It's a few more than
Really?
200 yards.
Yep.
As proposed,
It was-
1,400.
That's
Yeah.
weird, because I
That
went
was-
up there and they have a little museum.
Well, they had 2 locations, one in Michigan and one in Wisconsin.
Oh.
And they were connected, so between the 2 of them, there was 84 miles of antenna.
Oh, so you almost had a partial antenna here, partial.
Yeah, but they were linked, so they worked.
Yeah, that would make sense.
Yeah.
I just remember they had a little mock-up of it. It looked like telephone lines,
Yeah.
but it's not telephone lines, it's an antenna.
Proposed was like 1,400 miles.
Yeah, proposed said, the proposed system would have a giant antenna consisting of 6,000 miles of buried cable in a rectangular grid covering 22,500 square miles. Powered by 100 underground power plants. 100?
How many power plants?
100.
What kind of power
That's
plant?
weird.
That was to survive the nuclear attack.
Yeah.
Oh, is that why?
Yeah.
I'm looking back through my notes, I'm like, I gave you the speed of light. Was I supposed to tell you how long that wavelength is? I don't think we got there yet, it's wild. Iceman.
Hi. I'm good.
Yeah.
What's going on?
Alright, that's coming up. Got a lot of words on my notes right now. I'm like, oh, I think I missed one. It's all good.
It won't actually be long, but it should feel like it. It's gonna feel like a normal rain day. Yeah. You guys back tonight? Except for, what? You guys back tonight? Heck no, man, I gotta work tomorrow. Brian, you know, he's sitting there farming all day. So they got a plane and crop dust or something? Yeah, that'd be cool.
Is crop dust thing gonna die?
Yeah, drones are starting to grow. Think so? You know how many gallons those drones can help?
I
They're
watched
a lot
it.
cheaper to maintain.
They're making bigger ones. I think part of it is I've seen videos of, they'll have 2 guys operating the drones off like a semi bed, and one will come back and they refill and recharge it, and it goes out, and then the guy refills and recharges the next one. So like, it's not as many gallons per drone versus airplane, but when they'll have like 6 of them out in the field with one guy refilling, and they can just crank it.
My buddy does surveying for a spraying company that has the drones that go to a little drone that goes and checks to make sure that they can get in and out.
Yeah.
And he says that with where it's at right now, he doesn't ever think that it will replace it. So he works for a spraying company that does that. He also is, they're family friends with the owner
is it's a hover drone, right? They're helicopters. You could get into a lot smaller spaces. So it might be something where it's market share, where because they can do better, be more accurate, they start edging out the other guys, and it makes it harder and harder for the other guys to make a dollar in business. So that was one I heard. There's a place over in Grand Haven that does spraying Hatfield. Every time I drive by, I'm like,
We've got,
gotta stop in and see if I can get a job.
we've got a family friend,
One or two Christmases ago.
yeah, he started a company,
That like had the
bought like a
spotlight.
box truck, got AC in it, like 3 TVs, and then they pull a trailer with the, they've got like a 5,000-gallon
Okay.
tank on it, and then a flatbed where they land.
Yup.
Then they got a ramp, so they walk out the back of the box truck, fill it up, swap the battery, go back inside, the TVs inside the flying.
Wow. Yeah, it's
Got
pretty.
That was not what I
certification so
thought.
you can fly at night, fly multiple drones at once.
Oh, really? Yeah, 'cause that'd be a game changer. There's nobody doing crop
I always
dusting
forget
that's out there at
what
night. Yeah. I think, I'm not a southern or western guy. I think when you're talking crop dusting out there, it's just a vast acreage. Like, that's part of why they're doing it instead of driving a tractor, right? It's just too many acres to drive a tractor across. So, those ones would probably be trickier for a drone to take over, but, yeah, you see the, what do you, what's one of those crop dusters cost, $2 million by the time it's $1 million engine, right? So I don't know how many drones you can buy for $2 million, but, probably a few.
Yeah.
So that's where you go, hey, can I buy 10 drones for the price of one crop duster? Yeah, I don't know, I'm not a drone guy. How much maintenance? I mean, they still have a motor, but you can probably swap the motor.
How much?
Barely anything. You don't need a regular drone.
Yeah, you don't need any like drones. Yeah, I guess they don't have all the flight. Yeah, that's a good point. They don't have flight. They don't have flight control per se, it's just speeding up the
And he
motor.
ran out,
So,
home run.
there's kind of less rate than that. Like, you think through it that way.
Like, you're going across the road.
Right, yeah. Just some bearings. All right,
Maybe a short between the wires.
yeah. It's less efficient. Is it less efficient to fly with a? Yeah. You have too many wingtip vortices. My question would be with that, will they get to where they're flying fixed wing drones for crop dusting? That sounds scary.
I don't know if that would be more cost effective though. I feel like the drones are just cost effective.
Well, the electricity or fuel costs go down. It's more efficient to fly on fixed wing. I don't think the technology's there to land a fixed wing drone, loaded, unloaded, short strip. Definitely.
The military's probably got it, but
Yeah, much more.
All right, we are back to my favorite part of this class. How electrically the antenna transmitter actually works. So, what we're gonna do is we're gonna draw a wire split in two. So that's what we basically have drawn here. It's a wire, but we put a split in the middle. So we cut it in two. Now we're gonna feed this wire with a coax cable. And here's the part you're just gonna have to trust me on, because if you try to think about it and figure out how it works, either you're gonna be smarter than me, or your brain's just gonna melt. But in our coax cable, if I were to draw my coax with a center conductor and an outside conductor, if my electricity, maybe I should draw it on the side. If my electricity on the center one is going that way, but my electricity on the outside one is coming back the other way, when I use my right-hand rule, because it's a coax, the amp draw cancels any EMF field out, right? Because whatever EMF field I would have put out from my middle wire is going to get canceled out by the other one, because it's going to do the exact opposite field. So, just trust me and believe me on that one, that basically any coax cable that we're feeding our antennas, we just don't consider it to be anything. We're just like, it's like it's not even there. So whether I hook my transmitter or receiver up here, or whether I hook it up over here and run a big long coax cable, most direct route, so that would be a bad drawing, I guess. But we are just considering that essentially we're hooking up our AC system directly at the break, and just figure the coax cable is not doing anything. If you really want to get deep, you get into, well, there's a certain resistance in the cable and blah, 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 we'll talk about later, but I'll start to lose you at that point. So just figure the coax is nothing. We've got a wire, and there's a break in our wire. Same with this. So we call this kind of antenna a bipole antenna. Basically, we've got two tips of our antenna. You might say we have two lengths of wire even. They don't like to say that because they actually just like to say that we break it and put our coax in the middle. But bipole antenna, really what they're after is there's two tips, bipole. But you get the point. Here is dipole. Did I say bipole?
Yeah.
Bipole, dipole, two, dipole. Double pole, sorry. How do I get the bipole? It's a bicycle. So dipole antenna. So this is drawn with it, same idea. You got the wire here. This whole section would be considered the coax coming to it, right? So once we have the coax, we say, hey, we're just going to ignore that coax piece. Here is where, well, I'll go back one. On this, if we were to have it here, or even, I'll just draw one up. There's my dipole antenna coming down to an AC, that was a bad sine wave. AC, this could be a generator, we go into digital, we're not gonna get that far. But basically, if this thing is trying to move power this way, what's going to happen on my wires? It's coming this way on this one, it's going that way on that one, and all of a sudden you go, oh, that's interesting, isn't it? Because if I use my right hand rule, my magnetic lines of flux are identical on both of them, so they're going to add to each other. It's going to basically say, ooh, I'm now going to radiate whatever field with my fingers, it's going to radiate out. As opposed to if it was set up like this, I would have one field with the north-south going towards me and the other switch. So the interesting part with these dipole antennas, and basically any antenna, is if they're agreeing with each other on which way the amp draw is going through them, basically you're like, okay, it's one antenna doing one thing. And we'll get into a little bit deeper how it's slightly more complicated, but that's the very simplest version of what we're looking at with these things. All right, here's where things get a little bit hard to fathom, and I might have even said prep work question was no good until I totally got it. There was one, I think it was in a totally different class, where it was asking about lambda and wavelength, and I was like, you don't need that. And basically it was because you don't need it until we get to antennas. They snuck the question in the wrong section is what happened. So this symbol here, Greek symbol, it's hard for you to read back there probably, but lambda, L-A-M-B-D-A, lambda, that is basically saying wavelength. And it's going to be in a couple different forms that we use it. So you see in our formula, lambda is wavelength. And the reason we're going to go with wavelength is what I'm explaining in the next couple slides. But our formula for how long our lambda is, you can say how long our wavelength is going to be determined by the velocity being the speed of light and the frequency that we're modulating back and forth at. Our velocity, we're going to just assume it's 300 million meters per second. We're just gonna go with 300 million. We're not gonna split hairs and go, am I in space, am I in the atmosphere? I don't care that much. Just 300 million is gonna be a good enough number for us. So, basically we've got this AC generator down here. And I'm gonna just draw my antenna. I'm gonna ignore the coax cable going to my generator because we said we kind of ignore it, right? So if I start my AC generator and I say, hey, we're trying to send electrons in that direction there with my arrows, they're gonna travel at the speed of light, right? 300 million meters per second. But the frequencies we're using for our radio are so high that before even the end of this antenna gets the signal of, hey, we're trying to send power your way, I might reverse it. You're like, you're crazy, Case. Light goes faster than that. And I'm like, well, let's check the math and see what we're doing. So let's do some math for 122.8 megahertz. That's our frequency here in Ionia. So 122.8 megahertz. And we're gonna see what lambda is. We're gonna see how long basically our radio wavelength is going out. So 122.8 is up in our VHF range that we communicate at, right? Megahertz, mega, is 10 to the 6th million hertz. Oh boy. So I'm gonna draw some zeros out here. And I gotta move it over. We said 6. 1, 2, 3, 4, 5, 6. Drop my decimal in there. If I was gonna put commas back in, 1, 2, 3. 1, 2, 3. Oh, that's convenient. Our formula for lambda is velocity. So we're gonna do 300 million divided by our frequency. And that's going to give us what our lambda is. And somebody's probably quick on the calculator, but probably going to be about 2 meters. 2.44. Okay. 2.44 meters. So basically, at 122.8 megahertz, at the speed of light, that electricity only gets 2.44 meters down a wire before, I don't even want to say it's reversing because it's actually a sine wave that's going this way, right? So you got a max voltage, minimum voltage, and you could keep going. It's actually between, the two positives, apparently we're doing AM. Between the two positives is 2.44 meters. So it's actually, if you wanted to cut it in half, between the max positive and max negative, we're back to 1.2 meters. So, wow, that, for me, that kind of blows my mind that the lambda, and you'll see why that's important shortly, the lambda is switching back and forth so fast. And that's for our radio comms here at VHF, 122.8. You get up into the gigahertz, and it starts getting really, really short, how fast the signal is going back and forth. That was just my math. All right, so back to our dipole is two-pole. This is also known as a Hertz antenna. When we say dipole, you could say it's a half lambda antenna, or you could say it's a dipole. The reason for that is the length of these should be 1/2, I don't know how to draw that, lambda, L-A-M-B-D-A, yeah. The length of that dipole should be either half lambda or however else you want to say that, so Hertz antenna. And we're going to see why shortly. The idea is if I have my antenna, and if I make it too long, so that I've got a positive voltage going on in this section, but I got a negative voltage going on in this section, basically the EMF from each section is going to cancel each other out. And when I say voltage, what we actually care about when we're doing the right-hand law, do we say voltage or amperage? Amperage, right? So it's the current. So it's actually, if I had a positive amperage here, but because this one's too far down the line with my reversing, and remember our static, they tend to stack up and not, it would cancel the signal out. So what we do is we size these antennas so that each one of those legs essentially is only seeing a small section or part of our sine wave that it's, oh, it was positive, now it's negative. So the perfect size for our antenna is a half a lambda, and we're going to see why that's important here shortly in the next couple slides. Alright, so if we look at, and it's going to be hard to do showing you guys, but I'm going to try it. If we look at our antenna here and say we're going to be sending out a positive signal and then a negative signal, that it takes a little bit of time for this positive signal to travel down the wire, right? It's going at the speed of light, but it takes a little bit of time. So if I turn my AC generator on and I say, hey, let's get to maximum positive. We're going to simulate maximum positive with a red marker. I'm going to simulate maximum negative with a black marker, basically. But if it takes a little bit of time, basically what happens is at like 0.1 in time, they might both be here coming out of the generator, but they're going to travel out, and at half the sine wave, they would have made it out to the end. It's actually quarter time. And then they're going to come back at a quarter time to come back to no voltage. Let me draw this on a timeline. So at 0 point, you could say they're in the middle if we're looking at the end. At a quarter voltage, I've got a maximum. And then the next one, they're back into the middle. And then I'm going to reverse fields, and they're going to go this way, and then reverse that way. So I got like a GIF, a little video that will show basically it's that power going out and the amperage associated with it, and the timing of why our antenna has to be just the right length. Okay, let's see if it works. So what they're trying to show in this one is the voltage is in red, and for whatever reason you actually don't have much voltage here, but in static, remember, it adds up and it'll want to go out towards the tips. So the voltage at any, let's say, given point on our antenna would be red. What actually sends out an EMF field, though, if we're using the right-hand rule, is our amperage. So what's weird with antennas is the amperage, as stuff gets stacked up and not stacked up, is the amperage will be highest in the center part of our antenna. Basically, the way to think of it would be, if I was to come over here and give you guys kind of a push, and we started stacking up and bunching up, and I was like a boom, and sent that wave out, what's going to happen is I'm going to move more of you that are close to me because you're closest, so you're going to get a higher amperage in closer. As you get out to the tip where you can't move anywhere, we're not really going to move many of you. That might be a funny way to explain it, but the main one is you're looking at, because it's opposite directions of those current flow in there, the signal off each leg is going to basically be saying the same thing on this side as it is on that side. So that's basically what's going on our antenna as we reverse current. If you want, you can check the internet on break. Try to get somebody to get a different video that explains it better. Good luck. I spent quite a few hours. but you might find it, and we're gonna go a little deeper. But that's basically what's happening, and you're looking at what color is that, blue? Is that blue or purple? Purple? You're kind of looking at the purple, in your head you're thinking, if that's my current, then the current's gonna induce an EMF wave, an EMF field, that's gonna get sent out into space. So you can kind of picture the purple being the EMF wave that's sent out into the air, into space, or however you want to phrase it. So if I was gonna make this side of the antenna longer and put it out to there, oops. That's not what I want. Maybe I put it here. I won't do it. It would do it when I wasn't in display view. Anyway, you would end up where, I'll just draw it in. So right now, if I was to stop time, you would actually end up where if I extended the antenna, the amp draw would be back to the other side because of our lambda length, our frequency length. And if that was the case, if I looked at that section of antenna, I'd be getting a signal from my fingers one way coming off this side, one way off that side. They're going to cancel. So let's say I extended it just a little bit. I made my antenna just a little bit too long. It's still going to work as an antenna, but there's going to be a little bit of inefficiency. So we can use one length antenna to do multiple frequencies. Like our VHF antennas on our aircraft, we're not changing the length exactly, but we lose just a little bit of either efficiency or capability by having it be just slightly off from a half a lambda for a dipole antenna. So as a reminder, what is EMF radiation? It's electromagnetic force radiation. There's a whole range of EMF. Basically, most of this radiation is just EMF radiation of what we're dealing with. So my chart that I put up here goes from 3 kilohertz up to 300 gigahertz. And if you were to do the math for this one, our very low frequency is down here on our radio waves. Our ultra high frequency that we leave off on is up here at 10 to the power of 11ths, get into GPS. If we were to keep turning our frequency up, keep cranking it up, eventually we get to where your eyeball is picking it up, and we call it visible light. And you go beyond that, and we get into X-rays and gamma rays. The frequency is just, your mind can't even fathom how fast and how short it is. But all of these are the same EMF radiation coming at you, and that's kind of why I say you live in a world of EMF radiation. It's a staticky world. There's a lot of radiation hitting you all the time. It's just you've got to tune in the correct frequency to be able to make any sense of what is going on with it. If you tune in a specific frequency electronically, you'll be able to pull out as it gets stronger and weaker just on that frequency. All right. Let's do the math real quick for a GPS antenna. So our GPS systems are operating at, I think they just give us a roughly, but roughly 1.6 gigahertz. And because we didn't teach the next time antenna, we're going to assume that you have a dipole antenna, and we want to know how long does your antenna for your GPS receiver have to be. So if we went back to our formula, there it is, velocity, we're going to go 300 million meters per second divided by frequency. GPS is 1.6 gigahertz. Giga is 10 to the 9, so I gotta go 1, 2, 3, 4, 5, 6, 7, 8, 9. Somebody got a calculator? Say it again. All right, 0.1875, and we started with meters. So because we're in a 0.1 and my brain has a hard time, I'm going to go with centimeters. I want to move this to a centimeter for me. So 100 centimeters in a meter, so I'm going to go 2 over. I think we're a digit off with your math, but we'll see here. So that would be 18 centimeters, and our antennas we want to be half that length, half lambda, which would be 9, but I think it's actually, well, 9 could be. Anybody double check his math? He might be right. Confirmation? Otherwise I'll do it real quick. Part of the problem is your calculators don't go up that high, right? What if I get rid of 3 zeros? Get rid of 3 more zeros. Get rid of 2 more zeros. 3 divided by 16. Is that right? 1 point? Okay. 0.1875, he's right. Okay. Very good. So, your antenna for a 1.6 gigahertz. Oh, you're right. Sorry. I was thinking cell phone. I jumped all the way to cell phone instead of GPS receiver. So your antenna for your GPS receiver is going to be, it's that 18 centimeters. But half a lambda gives us 9 centimeters long. So basically, 9 centimeters is about like this, right? 3 inches, somewhere in there, from our Canadian man. So, what's interesting is, you can look at what you're receiving and say, hey, how long should my antenna be? Now, we're actually going to cut that in half one more time, because so far we've only been talking about this dipole antenna. We're going to introduce a new kind of antenna called a Marconi and or a ground plane antenna, and those ones only have to be half as long. So we take that 9 centimeters and we drop it down to 4.5 centimeters. So if we go down to our ELF system, our very low frequency, if you went down to ELF and said, let's do the math, how long is our antenna got to be? A lot longer, a couple hundred meters or 1,000 meters, wherever it is. But in this range, basically we end up, for our VHF was, what's the math at? 1.2 for our dipole. So when you're walking around airplanes, what you'll end up noticing, and we'll do the math one more time on our comms, just because I want to show it to you on this one. So our comm antenna is going to be 300 million divided by 122.8. We got to move it over. Does anybody remember what the math was? 2.44 meters. Okay, cool. Was the full lambda. We're going to divide that by 2 to get half lambda antenna, which was 1.2 meters. And then what's really going to happen is we're going to divide that one more time by 2 as we introduce the next one to get a Marconi antenna. 1.2 meters divided by 2 is 0.6 meters, which, how many centimeters would that be? 600 centimeters, which is 2 foot. Coincidence? I think not. So there's your comm antenna. That's basically 0.6 meters long.
Where does it split there?
That's what we're going to cover in a minute. This one's only a quarter lambda, and we're going to figure out how they do that shortly. Great question. Because otherwise, we'd have to have like wires connected in the middle of it, right? Yeah. So that's the next thing we're going to cover is the next style antenna. Well, a little bit further down the road. All right. I am supposed to show you not the whole thing, but if you want to go watch this whole thing, it's very interesting, but it'll lose you at some points. So I'm just going to show you 130 to 430 of this thing. and it's going to show us radiating our EMF and some other stuff. And then we'll go back and talk about what that looks like. There's my mouse, 130 to 430.
Antenna. The ends of their paths, the velocity will be zero. The charged particles undergo continuous acceleration and deceleration due to this velocity variation. The challenge now is to find out how the electric field varies due to this movement. Let's concentrate on only one electric field line. And at the ends of their paths, the velocity will be zero. The charged particles undergo continuous acceleration and deceleration due to this velocity variation. The challenge now is to find out how the electric field varies due to this movement. Let's concentrate on only one electric field line. The wavefront formed at time 0 expands and is deformed as shown after 1/8 of a time period. This is surprising. You might have expected a simple electric field.
Sorry, I realized, I think they took it off. Originally, they drew your antenna here, and how I said you're going to get where the charge is going back and forth on your antenna. So what they're having you imagine is these charges are what's getting sent out, pulsed to your antenna from a AC alternator. So I'll give you that little bit of info, but it'll make sense as you go through.
As shown at this location. Why has the electric field stretched and formed a field like this? This is because the accelerating or decelerating charges produce an electric field with some memory effects. The old electric field does not easily adjust to the new condition. We need to spend some time to understand this memory effect of the electric field, or kink generation, of accelerating or decelerating charges. We will discuss this interesting topic in more detail in a separate video. If we continue our analysis in the same manner, we can see that at 1/4 of a time period, the wavefront ends meet at a single point. After this, the separation and propagation of the wavefront happens. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. If you draw electric field intensity variation with the distance, you can see that the wave propagation is sinusoidal in nature. It is interesting to note that the wavelength of the propagation so produced is exactly double that of the length of the dipole. We will come back to this point later. This is exactly what we need in an antenna. In short, we can make an antenna if we can make an arrangement for oscillating the positive and negative charges. In practice, the production of such an oscillating charge is very easy. Take a conducting rod with a bend in its center and apply a voltage signal at the center. Assume this is the signal you have applied, a time-varying voltage signal. Consider the case at time 0. Due to the effect of the voltage, the electrons will be displaced from the right of the dipole and will be accumulated on the left. This means the other end, which has lost electrons, automatically becomes positively charged. This arrangement has created the same effect as the previous dipole charge case, that is, positive and negative charges at the end of a wire. With the variation of voltage with time, the positive and negative charges will shuttle to and fro. The simple dipole antenna also produces the same phenomenon we saw in the previous section, and wave propagation occurs.
Alright, so I gotta pause that just to point out, this was the best video to wrap your head around. As you watch the electrons, you'll notice very low amp draw out here, right? Because there's nowhere for them to go. But watch them when they're going back and forth, and you'll notice in this section, a lot of the electrons go by. So the amp draw in here is high, the amp draw out here is low. But voltage, like right now, I have the highest pressure difference between all my dots and all my pluses. So the tips of the antenna will have the highest voltage, but the inside part of the antenna has the highest amperage as it's going. Leo?
So all we've been kind of watching is transmitting only?
Yeah. Yep. You'll get receiving shortly.
Charges will shuttle to and fro. The simple dipole antenna also produces the same phenomenon we saw in the previous section, and wave propagation occurs. We have now seen how the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. Since the propagation travels at the speed of light, we can easily calculate the wavelength of the propagation. For perfect transmission, the length of the antenna should be half of the wavelength.
Alright, made it to 4:30. So that's where I gotta stop it. If you go watch this, the next part, they get a little bit confusing because they'll draw, so this is a positive peak, that would, positive peak, negative peak, positive peak. And it would keep going out, right? So they'll draw it, and it gets a little confusing, but one of the things to know is we're very concerned that our length of our antenna is that 1/2 lambda, however I draw that. Each half of that is a 1/4 lambda, right? The distance in between my radiated EMF, because we're traveling at the speed of light, both our electricity but also our field travels at the speed of light. In between, you notice that what this is it's that magnetic side of the right-hand rule, the flux lines. Notice the flux lines are going up here, flux lines are going down there, flux lines are going back up here in each one of those. So when you draw that out, if you were to draw it as a sine wave, in between each two positives, that's going to be the same wavelength, or the same lambda. So when we're using the word lambda or wavelength, it applies both to our electrons going here, but also applies to our radiation pattern that we're kind of sending out from our antenna. So once you get that, what they're going to try to do next is they're going to say, okay, let's say I've got a wire right here. We're going to have it the same exact configuration we had before, but instead of a generator, I want to put a light bulb. What's a light bulb look like? I want to put a light bulb in the end of this thing, okay? I'm going to put a load. Now, reality is it's going to be a transistor that will ultimately amplify whatever voltage it sees. But if I use the right-hand rule here, and it's really hard to get on a two-dimensional board, but my right-hand rule of voltage generation, so current, induced. So right, left. Back to my right hand. So I'm back to my right hand. If I put my right-hand rule on this wire right here, what ends up happening is the wire will be my finger one way or the other. The electrical field is going to be which way I'm pointing my, this way, sorry, it turns 90 degrees. That way, that's why it's hard to see, the 3-dimension. So what happens is when this field with the north-south facing one way goes across, I get voltage generated, let's say in this direction. When that field that's opposite it goes by, and I'm struggling to figure out how does that go again, but point being, it's the opposite magnetic field, right? That's all you need to know. When the opposite magnetic field, and remember these are moving by our antenna. They're moving by, it's our flux lines moving by our antenna. When the opposite flux line goes by the antenna, it's going to reverse and do my power the other way. So it's actually the mirror image of what we're sending out is you're receiving it. And you can actually, they make a device, you can measure how many amps or how much voltage will be generated in the signal, but that's way above the level we're going to go. But so a receiving antenna, as long as it's in the same general vicinity for if you're transmitting, now we'll pretend there's a cut in the middle and it's a dipole, and I'm receiving, if he's sending out these waves that are coming at me, when it hits my antenna side, I'll actually generate a voltage out of that in the same way it's sent out. So it's an interesting deal. If you really want to go deep, Nikola Tesla was going to try to power the world with that system. Because you can send that frequency out and we'll send it on a distributor and we'll harvest it on the other end. I can't remember why it didn't work. We were all going to get cancer or something. I don't know. But People were scared of it. So, the answer to your question, Leo, is especially on these dipoles, basically the exact opposite of sending out the wave. As those waves pass across our antenna, it generates it on the other end. But it's going to be a lot smaller voltage, right? Because we're going to lose a lot to space. So we're going to have to receive that tiny little voltage and then send it through transistors to step it up so that it's usable. But,
So is that all tucked away in the same antenna?
well, this might be my airplane, and the other one, oh, you mean like,
The sending and receiving?
yeah, sending and receiving, correct, yep. Yeah, it's pretty hard to send and receive at the same time. When you hit that button, you're gonna basically not receive anymore. Yep. Okay. Next slide. Yeah, that's basically the same thing. That video gives a pretty good idea with them going back and forth of how you get to every other way. In reality, you'd have to draw so many lines on there that this is just showing you the maximum kind of pulse, if you will. There would be other lines, you can find other pictures that have the full, like if you were to throw iron ore in there, right? The full field. This is trying to simplify it so that your head can be like, okay, here's my maximum pulse, and then here's my maximum pulse the opposite direction.
So, considering the amplitude changes, what would that look like, smaller versus bigger in amplitude on that wave?
Yeah, you couldn't necessarily draw it here. It would be when you pick this up with your antenna. This wave might be stronger than this wave. Might be stronger than the next wave or weaker. Yeah, so each one of these is one of those. So if I wanted to turn the amplitude up on one, I could turn it up, and then I could turn it back down, and then up again. So I can't draw stronger in the picture. It would just be more EMF force. Because they're going to travel at the same speed, because that speed they're traveling is the speed of light. The distance between each one of those, if I was to crank the frequency up, whoa, that means these are going to get a lot tighter between positive, negative, right? All right. So here it is in a little bit simpler form, but here's our generator generating the pulse that's coming out, and here's our receiver that's basically taking that same maximum and receiving it. That's going to induce a voltage on the other side. I do have to remind you before we take a break, we're dealing with an EMF wave, electromagnetic, and I was going to try to explain how it works, and I'm like, no, we're not going to try to go there. It's part of why I can't get the right-hand rule to work right, because you got to switch back and forth between electro and magnetic. But the magnetic pulse or field has a kind of dimension in space, kind of like a wave has an up and down. The magnetic has a dimension, and the electric has a dimension, and they're 90 degrees from each other. So there is a piece of, if he's one antenna and I am another antenna, they don't work the best if I do this. If I turn it this way, the 90-degree form he's sending out, I don't receive it very well on this one. If I'm anywhere other than directly perpendicular, I'll still get a signal, but this would be the weakest. This would be the strongest signal because I'm aligned in space the same direction. So it's kind of important to realize that. And what you'll end up noticing is on our aircraft, a lot of our navigation antennas that are operating, where's my slide? A lot of our navigation antennas that are operating at very similar frequencies to our communication antennas, but a lot of our navigation antennas will be laying on their side, where our communications antennas are typically vertical up and down. And they do that just to kind of give you some separation of what we're doing. So when you look at the tail of an aircraft when we come up, if you've got laying on their side antennas for VHF, it's probably going to be for navigation. If you've got a vertical, it's probably gonna be for communication. So they change which way they go. I'm not gonna get too deep into that, but, it is a piece of the puzzle that there is a dimension to that. I think I have a slide later that explains it with light and polarization. But we'll deal with that after a 6-minute break. What slide am I on? 6-minute break. Come back at 1:45.
So how do these waves work with mountains?
They don't go through them.
No, but do they come back down through, like?
Well, no, it's line of, we're pretty much line of
Fairly
sight.
line of sight,
Yeah. As you get lower frequencies, they can kind of get bent off, like atmosphere changes. I think my understanding of that, and I'm not sure on this, I think my understanding of that is if the air's thinner up here, it's gonna travel faster because it's closer to a vacuum. So it actually would accelerate this portion of your wave, which is gonna then tend to basically turn it back down, right? So that's my very, very rudimentary, if we were to draw the curvature of the earth and say vacuum up here, thick atmosphere down here. If I send out a wave, I'm gonna send it like this. If I say I'm sending it out, it's not gonna just kind of leave into space because it's actually up by my vacuum travels faster. So what happens is this top of the wave starts bending over and then it'll basically follow. Yeah, that's how I understand it to happen. I think it's fairly accurate. If you get a crazy high frequency, it's not as easy to bend it, so higher frequencies will just shoot out. Lower frequencies will tend to get bent easier. I'm not 100% sure why that is.
How do they kind of stay in that atmosphere?
Yeah.
Lower frequencies
Lower frequencies go through water better, yeah. Or they'll, yeah.
So you think that those are the ones that would escape atmosphere easier?
Well, yeah. Yeah, you think they'd just leave. Yeah, that's where I say I'm at a very rudimentary level of why they follow the curvature. But it's something like that.
Okay, why does this thing gonna work is money bait, there's no way to target it.
Oh,
It is super, it is super interesting to do that.
But it's such a cool
It
concept.
is so cool, it's one of my favorites, actually, I wanna test my foil so bad.
So, my understanding of it, kind of way off topic, but if here's my transmitter and I'm sending out, and here's my receiver, I'm only picking up a certain degree. So what gets weird in my head is the rest of this all weight, like, back to the conservation of energy, right? I get that if I just pling the thing, it'll stay established there, but there's some sort of interaction here where when you induce an amperage, it takes work to do that because you're moving stuff. So somehow the fact that you harvested it, I don't know if it slows down, like how, if I got 10 people with these sucking power off, with the law of conservation of energy, somehow my generator would have to, through those fields, essentially feel it, and it's gonna have to work harder to make it. So we can't make free energy. So,
Sound doesn't get quieter the more people like this. Yeah, it's cause you're not pulling straight from the source, you're generating it and pushing it all out in all directions, so you're giving like the same amount of energy in all directions, so no matter where you're at, you're getting the same amount of energy. Does that make sense?
well,
So like,
kind of.
see that?
The closer you are to it,
No, that's not good. So like, it's giving you like 10 volts this here, and 10 volts here, all the time. So
Yeah.
if a person's standing here, then and here, with their little light bulb. It's gonna give you 10 volts here and all the
If we're opposite of our dipole antenna, for instance,
Well, it'd just
as
be,
it's,
it would just be like slightly out of phase.
yeah,
It'd be like,
180 degrees.
yeah, but that wouldn't affect it. This one would affect the negative.
Well, it's
So if we did
10
that-
volts AC, so at a very,
Yeah.
very specific time,
So
the
if we did
opposite
that-
side will be the exact opposite voltage
Yeah.
in that very,
So if
very
it's the
specific
same
time.
distance away,
Yeah.
this would be negative, or that one would be negative 10, this would be positive 10.
Yeah.
And that-
So it might be that it's balanced if you got, it'd be weird, I don't know how,
That's why it's inefficient though, is because it's putting out 10 volts in every single direction.
Nope.
So no matter where you're standing, you still have that 10 volts.
but yeah, it's a weird, weird world.
It's almost like a Tesla married.
You what?
You married a Tesla.
Transformer to where the magnetic lines, flux cutting across the wire, reduces the voltage for signal.
That's exactly what it is.
Right?
Instead of soft iron rods around the wires, it's the hair.
Boston, dude. You know about the radar system?
The what?
Massive radio, like 800 yard pole, 150 yard pole. They have like a radar antenna. You have no hearing this.
Haven't heard of that one.
And if two people talk at the same time, you get like basically you're constantly sending out frequency. Yeah. So you can. Okay. I think you gotta have yeah, that big. Another guy wanted to do
By number of slides, I was only halfway through. That can't be. That can't be.
That's not the case.
I started clicking through them. I got a lot more. I got a lot more. Look at this one. Look at this one. Which is good. You've learned most of what you learned.
Typical PCE and what we're gonna have.
All right, we are, was that the break we were on? Yeah, that was the break we were on. All right, so we are back. So we're gonna shift gears a little bit and we're gonna switch antenna styles. We've been talking dipole, just assuming every antenna is a dipole so far. There are different styles of antenna. So we're gonna learn about a monopole antenna. Dipole is 2, monopole is 1. And we're gonna learn about a loop antenna. Loop antennas are highly directional sensitive, and we're gonna learn why. So, been talking dipole, we're gonna switch to monopole, and also talk about loop. So if you read in your book this part, it makes it sound like they're all bipole antennas. The reality is probably mostly actually monopole or Marconi. When you start putting stuff in like a vellum, which we'll talk about later, it gets a little confusing on, is that my 2 halves to my dipole, or is it 2 monopoles? When we have 2 antennas, one on each side of, for instance, the vertical stabilizer, if I wanted to say I want to send the same signal to 2 separate antennas, it does not work well for transmitting because stuff kind of gets messed up. But if I want to have 2 antennas and connect them to the same coax cable, for receiving it can work. It can work pretty well for receiving, but for transmitting, not so well. So I want to touch on that, and then as we go through some of these other style antennas, it hopefully will show up and you'll say, oh, okay, I see what's going on. But splitting one and having multiple antennas on one generator only typically works well for receiving. I feel like that slide got out of range. Hopefully we come back to the point. But we're going to talk about the monopole, which is a monopole. You might call it a Marconi because he's the guy that kind of came up with it. If you do a Google search for Marconi, you're going to get lost in the woods because his Marconi or ground plane antenna is going to be used more for like CBs and lower frequency stuff. But because he was the guy that basically figured out, hey, I don't need both sides of my dipole, I can actually make this work with only one side of it. His name stuck, so we get Marconi antenna. So if you see Marconi, what you need to, in your head, say is, okay, it's not a dipole that's a half a lambda. It's actually a quarter lambda long. It's only half of my dipole antenna. So whether you want to call it mono, whether you want to call it Marconi, and we're going to teach you why we call it ground plane here shortly. I still feel like I'm out of the slide, so here's what I'm going to do. I'm going to blank it off, and I'm going to teach you. So if I was to draw a dipole antenna on its side, we kind of covered how that works, how it radiates, right? Marconi figured out, connect this to my AC generator or alternator. Marconi figured out that instead of doing this, if I take that side, still have the wire, if I actually just hook it up to ground, the antenna will still function. Basically, if I was to draw a direction like this, I'll still get an amp draw in half my antenna, and it'll be the opposite, pulling it from ground or from earth in the other opposite half. So knee-jerk reaction is, oh yeah, I guess I could see that still working. It's going to be half as strong, right? I have half the antenna. But the kind of half genius of Marconi was, if we actually, when we say connect it to the ground, if we mount physically our antenna on the ground or run out some wires that are electrically grounded, as long as, maybe I'll draw it in green. As long as whatever ground surface we hook this thing up to is at least a quarter lambda in length, the signal that gets radiated off this thing actually has this weird effect that it bounces off the ground and adds back to it. Bounces off the ground and adds back to it. So it bounces off the ground plane, we call it, and the signal coming off a Marconi antenna is actually basically just as good or closely as good as if we do a dipole. So what happened was, instead of mounting an antenna that, let's say you're trying to use a CB and communicate with somebody and you're at like 10 meters high, you're going to go a really tall antenna. So if a quarter lambda is 10 meters, if you were to use a dipole, you would have had to have a 20 meter high antenna. So he figured out, hey, we can make our actual antenna out in my backyard when you drive by those guys' houses. I can make that thing half as tall by just connecting it to the ground and making sure I'm connected out there. So that's why we call it a Marconi, and or you might call it ground plane antenna, is we just take one of the legs and we go, we'll connect it to ground. How that ends up factoring in aviation, and the antennas we use, is the antenna coming off your aircraft is going to be a quarter lambda long, and the other side, that would have been the other quarter, just gets hooked up to ground. Now, on a aircraft that's made out of aluminum, that's super easy to do, right? This thing is screwed onto the aluminum, which is a great big ground plane, basically, and we go, I'm done, easy enough. I've got a Marconi antenna now. prep work question calls this a canted antenna as well because they're just trying to really confuse you. But this is a Marconi antenna. It is a quarter lambda antenna. It is a ground plane antenna. And this one happens to be on an angle, so to throw one more at you, canted. But, so, it's connected to my aircraft skin, which is grounded, so I've got a ground plane antenna. Let's say I mount this on a Cirrus. You're a Cirrus now. Oh. But my Cirrus is carbon fiber. Ah, snap, I don't have a ground plane. So what they'll do on your Cirrus, your carbon fiber Cirrus, is underneath where your antenna is, they'll put out a metal mesh. That's basically got to be the same quarter lambda length so that my signal will bounce off that ground plane and still work. Because you need two things. One is you need, I'm going to call it the static bucket for the electrons to go in and out of. But you also need, for it to reflect well, it needs to bounce off that. Now, right after I said that, when you get into crazy antennas, I believe they figured out how to do it without a ground plane on smaller stuff like cell phones and whatnot. And I think part of it is they just accept, I'll be half as strong. And I'll work with the half signal or whatnot. But in aviation and all your FAA books, it's pretty important, and it might just be a level above me. It needs to be grounded on the other side, and you need to have that ground plane for your antenna. So that's a Marconi. Now, this little guy with a whip, we'll call it a whip antenna because it's kind of springy, right? I can whip you with it. I don't like it, but that's why they call it a whip antenna. With the springy deal in there, for some strange reason, when we send out our electrical signal through this thing, it gets out to that, and it's like, whoa, all of a sudden, now I gotta run around there a bunch of times. When I finally get through, now I'll continue out. So if without that coil in there, this thing was gonna have to be, and we'll go with the dimensions on the board, 1 meter, about a meter, in the neighborhood. Let me go back. If this is 1 meter with the coil, if I uncoiled that, you'd say, hey, maybe that is 1.2 meters. So they'll call that a couple different things. They'll call it a coil. If you get into antenna theory, it starts messing with what's going on inside your antenna because we basically just made an inductor, right? And we already know our antennas, they have to be balanced, so when we twang them electrically, the capacitance and the inductance is balanced. But the engineers take that into account, blah, blah, blah. Long story short, they have figured out that if I needed an antenna that was going to be 0.6 meters long, but I don't have that much room or I don't want to make it that long, I can wind a bunch of it up to shorten it. And it's not going to be as good of an antenna, but if my receiver, my sender, if my computer system is good enough, it'll be like, you know what, it's still the correct overall lambda length, unspooled, so I can kind of compress it down and it'll work. It's just, it's not picking up as good of a signal, because if it's a full length, I got a whole meter to receive. If I were to coil this up so now I'm only half as much, I basically don't have as strong, I don't have as big of a wave hitting me to receive that. So when you see a coiled up one, what you got to realize is the actual length of it, you'd have to stretch that out to say, hey, how long is my antenna for what frequency? And it gets a little bit weird the way that inductor interacts, and I'm just going to drop it at that point, because otherwise it gets too complicated for us. When you put a bend in the thing, that's another way to just kind of warp your brain, because you're like, I just messed with the signal going out, right? So part of that, if you went back to those videos where, you know, essentially you're going to get a field coming off that one, you're going to get a field coming off that one. Essentially, that was neat and tidy on the screen, but you're going to get to where it's an average coming off that thing. The farther out from it you go, the less that bend's going to matter, because it's averaging that signal going out. So when you get a bend in it like that, basically as you get a little bit further from it, we're gonna be getting the average coming off it. So a little bit of a bend's not the end of the world. If it were to bend like this, now we got a problem, right? Because now, if I was gonna draw my lines, I've got this way, that way, this way, and that might fight it. Well, what's really interesting, as I introduce you to the next type of antenna, which is a loop antenna, what's really interesting is, well, wait a minute, what if I do that, and all these have a certain lambda, certain wavelength in between them, right? If I put this bend so that I'm exactly 1 lambda, or if I put it 2 lambda, do the same thing, away, the signal coming off this one, I don't know if I counted right, but if I space that loop exactly the right size, these two are actually going to add together as it goes out, because it's going to take time for the charge that's here to run around to this side, right? It goes at the speed of light. So what they do is they take your loop antenna and they're like, if we size this loop correctly, we can actually make an antenna so that the waves coming off are stacked exactly on top of each other. So once we get into that kind of idea, I'm going to say it's a loop antenna just for simplification of one side of my loop, second side of my loop. Maybe I should grab this circle. You guys can work with me, right? Pretend they're connected. Yeah, we'll go with this. So if I got my loop antenna, it's going to be very directional, right? Because especially if I'm sending a signal out, if I'm pointed right at Gavin with both my loops, the strength of that is going to be super strong pointed at Gavin because I'm stacking up both of those. Now, if I turn it this way, I am putting power down one side and back up the other side if I have it spaced perfectly. And all of a sudden now Gavin's not going to get any signal if I have basically the distance between each side of my loop if it's a half a lambda mathematically. So they will space a loop to be exactly the right spacing between each sides of the loop so that when I'm pointed at something, I get a super strong signal. When I'm 90 degrees off, I get no signal. And all of a sudden I go, well, that's interesting, because that means if I'm a receiver, super strong signal. No signal. All of a sudden, I can tell where the radio station is, where the radio tower is. Now, there's one problem with that, in that basically we're going to use the no signal to tell where the tower is, because a really strong signal, believe it or not, doesn't help us too much. So it's kind of a weird thing. But, so I'm actually going to use the no signal to say, oh, Gavin's that way. But the problem is, if I, there, I got it. All right, so Gavin's this way. Oh, really strong. Uh-oh. Also, no signal to Gavin, right? So I've got 2 dead spots. I got 2 nulls, so I'm actually not sure which one of those 2 directions Gavin is at. So if I only used a loop antenna, there's 2 possibilities of where that signal's coming at me from, and I'm not sure which one it is. I don't know how many slides later I gotta pick that up, but we're gonna pick that up with our direction finding antennas shortly. But quick review. Inside some of our antennas that might be mounted on an aircraft, you might have a dipole inside there. You might have a monopole inside there. So if all they were to give you was the outside shape of it, not 100% sure what's going on. So some of them, you might have to just kind of memorize what part of the aircraft they're on and what kind of part of space they're looking to receive a signal for. So without being able to see what the wire inside the thing is, it can get pretty hard to tell what kind of antenna we're actually at. So I gave you an airplane. Anybody recognize the number? some of you might like that, but it's actually the plane in a picture on the plane, and it's one of those weird ones where you can keep going further and further in the picture. Anyway, so there's our float plane before it got painted. But if I have antennas on top of the aircraft, now as I go around the aircraft, they're going to put out a signal. Here's my antenna on top. They're going to put out a signal to the side of it really well, right? So it doesn't matter where you are around me or which direction I turn, you're going to receive my signal. Now, if I were to turn my antenna and point it straight at Gavin like this, from everything we've been watching, my radiation comes off the side, right? So if I were to do this, Gavin's basically not going to get much of a signal because all the radiation basically happens perpendicular to our antenna. So we cant them a little bit. So these two antennas up here, there's a theoretically, if you were in exactly the wrong spot, kind of under me, down in front of me, I'm not going to pick you up really well with that, and I'm not going to pick you up really well if you're in perfectly the wrong spot behind me. In practice, that's not as big a deal as what it might seem. Here's an image they give you. It's showing, you can hardly see it, but it's showing you an antenna, and the donut is trying to show you essentially the strength of where you're going to get either a good signal sent out or where you would receive a good signal from, right? So if you're straight perpendicular to the antenna, and this might be miles or hundreds of miles or whatever, but if you're straight perpendicular, the signal's going to go out the furthest, it's going to be the strongest. If you're straight up and down from the antenna, it's basically a non-existent signal. So they'll call that the radiation field donut. They like to say that's the one on a dipole antenna. If you go to a monopole antenna, it's similar, but because we get that bouncing off the ground effect, it kind of messes with the bottom of the donut. But it's very, very similar. So, my comm radios, they're going to pick up communications around me very good. Are they going to be able to talk to, say, a satellite very well? Nah, probably not. So my satellite antenna is probably going to be tipped this way, and it's going to be mounted on the top of my aircraft. Because the other thing is, if I put a bunch of metal and people in between my antenna and what I'm supposed to listen to, is that going to work very well? No. So my GPS ones are going to be up top typically. Most of my communicating with the ground antennas are going to be down below, communicating with the ground. We'll get into that a little bit later, but oh, it's hard to see them. My whiskers back here for my ILS approaches are horizontally, because we said most of the time our navigation are mounted horizontally instead of vertically. So if I was to take this image and redraw it so that there is my airplane. I'm going to exaggerate it. I'll blank the screen off too. I'll exaggerate it, but usually I've got 1, 2 whiskers coming off there, right? And the idea is this guy, if we were to draw the donut, this guy is going to listen in that area very well, but he's basically not going to be able to listen in those directions, right? Well, guess what? This other one here, those are exactly the directions that he can listen in. So when we take our navigation antennas, the reason we put them usually at 90 degrees from each other is it's an overlapping field to say, hey, I don't have any real dead areas with my nav because I've split it so that I can pretty much see all around me. That's the simplified version, but that's why on our nav antennas, we will typically have 2 of them, and there's typically going to be a 90-degree bend in them to make sure that we don't have the dead zone that would otherwise be coming off from the end of our antenna. Distance measuring equipment, and I think it'll come up in a later slide, is probably going to be this one, and the reason for that is, remember our distance measuring equipment, it sends a signal out to a ground station, and it answers back, right? It doesn't like sending it through the wing. So if we were to put our DME on this one right underneath my wing, and then I turn my wing, and my wing blocks off that signal going down to the DME, well, that's not going to work very well. So typically our DMEs are gonna be hanging a bit further back. Now, a lot of our aircraft don't have a DME anyway, so, that's just an answer a prep work question. But they like to say not where it's gonna block off, with a wing. Now, if I wanna be on a glide slope, am I usually gonna be worried about a glide slope that's way over there? Say I'm flying this way. Do I care about a glide slope at an airport way over there? No, what's the glide slope always gonna be? Hopefully right? So my glide slope one will often be farther towards the front of the airplane, because it's looking ahead and it doesn't wanna get blanked off. It doesn't care if it gets blanked off by a wing, because if I'm on a glide slope coming down to a runway, I better not be doing this, or I got a problem to begin with, right? If I'm turning so much that I'm gonna be blanked off, I messed up my approach at that point. So typically our DME is gonna look a lot like our glide slope antenna on a lot of aircraft, but the DME will be further back, not getting blanked off by a wing, where the glide slope one will be more up in the front. So here's where it gets a little bit interesting. This is a form of a loop antenna. You can see it's looped around, right? This is the old form of a glide slope. So inside of, I believe that one, they would have often something that looked like this. It was a loop antenna. If I want to pick up a glide slope signal, remember it's actually 2 different frequencies, and if I want to listen to it really, really well, there's a real good chance that I want to focus with an antenna that's going to be able to listen in a certain direction really, really well, right? So a lot of times our glide slope are a form of a loop antenna, because when I'm on glide slope, let's say Gavin's the runway again, my airplane better be pretty much lined up with Gavin. You know, I might be in a little bit of a slip, but I'm lined up at Gavin, so I can use a loop antenna for this because my pattern is very directional. I'm coming down to the runway, a loop antenna works just fine. If I was perpendicular to the runway, I'm gonna have a hard time picking up the glide slope because, well, loop antennas don't work well for that, right? So your glide slope antenna is often a form of a loop antenna mounted up close on the front of the airplane. And what you'll notice is, see the frequency for glide slope, 328 megahertz, quite a bit higher. So a high frequency, is that gonna be a short or a long antenna? High frequency, short antenna, right? The higher the frequency, the shorter the lambda. So a high frequency glide slope, gonna be a short antenna. It's just a little, this picture's hard, but it's probably about that big, right? That little loop, you got about, I don't know, 6 centimeters, 9 centimeters in the loop. So up in the front, our glide slope that's got a high frequency is a short little loop antenna. DME is similar math, if I can phrase it that way. They tend to be those little shark fin guys or something close to it because it's a high frequency again. So high frequency, short little antenna. As we get to lower frequency, longer antenna. This particular one I want to touch on briefly. It looks to me almost identical, right? Can you tell the difference? Tough. What they're trying to show you when you get this picture is look really close. See those little holes there? I hate it. But, those little holes. Those little holes are supposed to be these holes in a glide slope. If you go out to the, I think it's the beach, the ILS, the navigation antenna, they'll be mounted kind of horizontally up on the vertical stabilizer, and they're big, they look like that. It's actually, they take the place of the whiskers. So if there's no whiskers, there'll be these like big plates, and those big plates will have some pretty heavy duty mounting holes to mount them. And unfortunately, when the FAA drew up their little sheet with different antennas on there, they didn't draw it very well. So this guy that's got holes in the side of it, it's supposed to be giving you the idea that, hey, this is a bit larger antenna that's got multiple mounting holes on the side of it. So sorry about that, but that picture's terrible. So this one we would be like, oh, it's a loop antenna. DME, Case told us our DMEs are little loops. That one you can kind of memorize. This one is going to be our nav antenna. I'm going to hit it in a couple slides. This is in a V shape, and so we're remembering when we're doing navigation, we like that V because it gives me coverage all around, and it's mounted horizontally. Our nav antennas are mounted horizontally typically, so that's going to say, hey, probably a nav antenna. So this one and this one, they're very similar, but they give us a little bit different. And then that one, you notice the cable coming out, that's kind of your clue that it's a small little guy, so it's going to be a higher frequency. So your cable coming out, small little shark fin, higher frequency, and you're going to go, well, must be my DME or my glide slope. Where is it mounted on the aircraft? Might tell you the difference. All right. Almost to, I think, another break or the end. What's going to happen with our ADF, automatic direction finding? Remember we covered that on day one? We got a piece of equipment that will point an arrow to, hey, where's that radio station sending it out? You got a question, Josh?
Yeah, probably loop antenna.
Yeah.
Do they ever make a loop antenna where they have the one loop and then they do another loop that's 90 degrees from it? So you can send, or does that just not work?
Not in aviation that I know of. But they do it the other way around, what we're going to talk about right now, which is going to be a little bit weird. So here is a standard loop antenna kind of radiation pattern. What they're trying to show you is green would be kind of like the positive, like if I took a snapshot in time with my sine wave with a plus and a minus. At a snapshot in time from either a bipole or a monopole or a loop, we're going to have where at one exact space from there, it's going to be essentially, it's a positive going off one way, right? And a negative going off the other. So they try to show you as I've got both the positive and negative effect of that wave. The reality is if I came in here with a pen, I could draw the next wave going out and the next wave going out, and then it'd be the other way around, right? Because it's back and forth alternating. But we don't want to confuse you that much. So they just took one specific wave at a specific distance at a snapshot in time, and they gave one of them, they said, okay, it's positive green, negative red, or whatever. So this is what the radiation field for either listening or hearing would kind of look like at a given point in time, as opposed to if you just had a monopole antenna, the field would be round all around it, right? If I had a field right here, it's going to say, hey, we're just going to give you one snapshot in time, and it would look like this. So what they figured out was, okay, this is kind of cool, my loop antenna, because I can go like this, strong signal to Gavin, weak signal to Gavin. He's either there or he's over here, right? Which way? Somebody along the time figured out that, hey, we're just receiving with these things anyway. I'm not trying to transmit. What if I do a splitter and I hook two antennas up to this thing? What if I hook a standard antenna and it ends up being a pretty long wire because our ADF, pretty low frequency, right? So it's going to be a long antenna. So they said, let's hook one just wire up to it. That would give us this pattern, basically, is what they're trying to say. Ignore the slant, because the slant's a little tricky, but you get the idea. And they said, okay, we're going to also hook up at the same time a loop antenna and give it this. What does the resulting radiation field look like? And it ends up looking like this, because the green is going to build on each other, and the red basically cancels the green because it's negative. So all the green from the bottom side of this one went away because it was canceled out by the red. So now I have a radiation pattern that looks like that. I've got a pretty good signal for most of it, but I got a definite dead zone in one area. You guys see that in that picture? One area has a definite dead zone. So basically now what I've got is I've got my loop antenna. I'm going to use my body as my sense antenna. They'll call it sense. So sense antenna. will be my body, and here's my loop antenna. And basically, it's going to cancel out one of these dead zones because of the way the shapes work. So now I'll only have, maybe I better go like this. Anyway, you get the idea. The next slide will show it better. It'll have one definite, I don't get any signal at all when I'm pointed this way, but as soon as I start swinging through these other quadrants, I go, yeah, I'm getting a signal. I'm getting stronger, 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 weaker, 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 weaker. No signal. So that's how our loop antennas for our ADF work. Now, hopefully somebody is asking this question, but maybe you're not. You might say, Case, you said we're at a frequency where it's got to be really long. How come we got right? Well, what they did in our loop antenna is they wound it up. So kind of like the whip antenna, they got wound up. They took my loop antenna and they wound it up on a sensor in there. That does a couple things. It kind of strengthens the directional, but it also shortens the thing. So this would be mounted on the bottom of an aircraft, and there's a motor that runs, and it actually spins the loop around. So the loop is spinning in a circle, so as it's going around, it's kind of like you would picture radar, right? As it goes around, and every one time around, it finds the dead spot. Oh, that's the dead spot, that's the dead spot, that's the dead spot, that's the dead spot. And that's what tells my instrument in the cockpit that, oh, that's where it's emanating from. So that's how the old-fashioned loop antennas work. There's actually a motor that's going to spin the loop mounted on the bottom of the aircraft somewhere. It's going to spin that thing around, but the loop and the sense have to work together to give us that funny shaped feel. You end up in the same picture here, so you got the sense portion of my ADF, and you've got the loop portion. They're connected electrically, but they're not connected physically. That took me a little while to figure out, so you're welcome for that one. Why it did is, anybody ever flown an airplane with an ADF? You have? Ooh, did it have a big old wire on top?
Yep.
Yep. I've never flown an aircraft with an ADF, so I've never seen that big old wire on top before. Now the closest to flying an aircraft with a big old wire on top is which aircraft, Micah? Heard you say it. 6 Mike Foxtrot. But 6 Mike Foxtrot's big old wire actually goes to the back and out to a wing. It's not for an ADF. It's for something else that's low frequency. Low frequency. 6 Mike Foxtrot is actually for my high frequency comm radio. So that's why 6 Mike Foxtrot has this big long antenna, is it has a high frequency communication radio built into it. Different system, not ADF. Alright, this is just a different picture. They tried to show you orange was sense antenna only, the red was supposed to be the loop antenna pattern, and the green was our combined pattern together. So it gives you a little bit different shape. The important part is we have one definite null. Null means nothing, nothing there. So when it says, there's nothing there, it's like, that must be where the tower is. In order to get a null, the system has to be like, yup, I'm picking up that frequency, I got the signal, oh, there's the null. Yup, I got that frequency, there's the null. Otherwise the needle, if it's always null, if you're not picking up the frequency, it doesn't know where to go, right? So you do have to have the, I'm picking up a frequency to give it a direction, but it's when that signal goes to nothing, okay, that's where it's at. Make sense? Okay.
Okay, aren't the loop antennas AC and one that keeps flipping back and forth, so the one here, on the same side?
Like you'd have a positive dead and a negative dead? I don't know on that one. Because the reality is, a little motor in that can, number one, ADF's old technology. Number two, that motor in the can and this rotating stuff, that kind of stuff breaks. So, what they figured out is they figured out how to do it electrically. They figured out how to basically give a loop antenna rotating solid state. So when you see these boxes that look like this, there's no loop inside here that's actually spinning. They're just going to do it solid state. So come take a check of those when you get a chance. But it's similar size, but basically what they did is they said, we're going to put a couple coils in there, and I got a fixed loop, and I got this guy, and I'm going to, actually that might be the old version, but they're gonna do it solid state-wise, and I have no idea how they do it. I'm not gonna bore you with the details, because it doesn't really matter. Because you're never gonna fly an airplane with them, most likely, unless you're Brian. Point being, this is the old loop technology where the loop's spinning. They figured out how to upgrade it to where we'll just do it solid state. And now, I am not 100% sure if they even need that big long antenna on top anymore, because once you went to solid state, the computer might be smart enough to say, oh, there's two dead zones, but I can differentiate between them. I'm not sure, and we're not gonna go that deep, because it doesn't matter. Mainly what you gotta understand is that the ADF uses the loop. All right, quick review on this. One prep question says that's a canted antenna. I hate it that they say that. All they mean is it's on an angle. It's a Marconi, which means it's a quarter lambda long. It's a monopole antenna, and usually we're gonna use this guy for communication. Glide slope is a loop antenna, and it's very forward-looking. I didn't put the labels up here, but those are gonna be our navigation antennas hanging off the back of the plane. GPS is typically gonna be on top of the aircraft. Remember we did our math, our half lambda, and then we go, oh wait, if we go down to a quarter lambda for our GPS, now we're only 4.5 centimeters, right? Something like that. They fit inside a nice little box, about this big right here, mounts on top of our plane so it can communicate with our GPS. So it's gonna be a little deal on top of the plane that's gonna be, roughly 5 centimeters long, up on top of the plane for our GPS. One question they like to ask you, I think everybody will get this on their written, is you don't have an antenna on your aircraft and you wanna add one. How much stress, how much drag is that gonna put on the aircraft? How hard is it gonna be to push it? How is it gonna try to rip the stress off? They will give you this formula, that's the drag formula. A is frontal area of it, so good thing they give you the math, because I'd hate to calculate the frontal area of that thing. So they'll give you the frontal area, and they'll give you how fast your airplane's flying. So somebody with a calculator, help me out a minute. If we said we had a frontal area of 0.15, and be really, really careful, the formula is in square feet. They'll usually tell you that, but one of your instructors might try to trick you, and he might put it in square inches. That was too big of a clue. I might not give it to you again. But if I do, what I usually do is I do my velocity first. So 250 times 250 will spit out a number. 250 is something. And then we'll take that number and we'll multiply it by my 0.15 square feet frontal area. And we'll take that number and we'll multiply it by 0.00327. Does anybody come up with a number yet? 3.06. All right, 3.0656. And that is pounds of drag is what they're going to tell you. So if you don't know how we got there by using the simple formula, come see me later. But I can tell you I'm losing you, so I'm going to just go quick through that one. You will have it on your exam. You will have it on a written. And be careful if they gave you square inches, square feet, or what they gave you. They give you the formula. You'll never have to do that without the formula. So it's just plugging numbers into a formula. Pretty easy. Oh yeah, 3.06 is what I got. 250 times 250 is 62,500. Yeah. Okay. Sheet metal shop. They used to have you make a doubler for O's and P's. I don't know if they do that anymore. I think they're having you patch holes more often than not now. But they used to have you do a doubler because it was a nice little sheet metal project. Well, nowadays, if you buy a new GPS antenna, usually you'll buy the doubler right with it. The idea behind the doubler is if I had a piece of skin and then I drill a big hole for my cable to go through, I basically just weakened the skin of the aircraft, right? And I can't just weaken an aircraft without remedying it. So I will often, on an antenna, I'll have another piece of metal that will bring back the strength to that skin that I just weakened by drilling a hole or a bunch of holes in it. So antennas should be installed SOT. So the forces are, wow, that is bad. I'm gonna have to fix that. Where's my notes? Apparently I didn't catch that one in editing. So the forces are transferred to the aircraft structure. Why it's in yellow and red is that's straight off some questions, but they don't want the forces transferred to the skin of the aircraft. They want it transferred to the structure, is how it's written. Now the doubler may or may not actually make it all the way to structure. Usually it should, but the questions will be stated so that those forces aren't just trying to rip the skin off, but they're actually transferred into the structure of the aircraft. So there's a little bit of discussion there, because there are doublers that aren't on a structural member, but if we have a choice, put it on a structural member. I'm going to go really fast through this one, because I don't think you'll ever see them, but up in the tail of an aircraft with our two monopole antennas, we might have a balun. They used to have this on O's and P's, where they'd ask questions about it. But here's your coax cable heading to the antenna. And basically what a balun does is I'm going to hook up one of my antennas to that one. I'm going to hook up one of my other to that one. And the other part is going to be grounded, because we're a Marconi or a ground plane or a quarter lambda, whatever word you want to use, right? What's weird with these is we actually didn't hook up the center wire, did we? Very strange. So the center wire comes up, goes through a little bit of loop, and it goes back here. They solder the two shields together back here. The distance between here and here, I drew it on the other side, is really, really important. They want it to be a quarter lambda. And the reason for that is, somehow by making this, they get away with hooking up just the shielded, because my center wire current is opposite, we're a quarter lambda, it's basically opposite in this side to that side, and I tried to figure it all out, and I was like, yeah, we're not even going to teach it. But if you see a question or somebody asks you about a balun, or you see something in an aircraft where it looks like, what in the world, they never hooked up the middle one, it's hanging out the end and it's soldered. It's because some electrical engineer somewhere figured out this works, and it makes two of my antennas, instead of having like a connection socket, it makes two of my antennas basically read the exact same thing. So they call it a balun. The distance between the split and where they're connected down here, aircraft ground, is crazy important. It's got to be the quarter lambda. So that's all the more I'm going to go on that one, because I think it's old info you'll never need, but it might pop up on a written or an oil. What's a balun? Like, it's a connection, and it's important that the length of it. This one's a boring one. A BNC connector. Yup, it screws onto an antenna. It's supposedly specific about being a quarter turn, I think. But they called it a bayonet, Neil Conselman. I tried to figure out why it's BNC, and I couldn't. It's some guy's name. So, some guy's name, it's a bayonet, it's a coax, it's a bayonet. Yep, so, I don't know how else to teach you that. Just memorize it. That's a BNC connector. We use it for coax. Oh yeah, that one. So our EMF is polarized, like we already talked about, right? Have you guys ever played that game with polarized sunglasses, where if you have them the same way you can see through them, but if you turn them 90 degrees, the light totally gets blocked off? If you haven't ever played that game with polarized sunglasses, that's how you tell if your glasses are polarized. There's actually slots in the glass where light goes through, but if you turn 90 degrees, the wave can't make it through anymore. So this slide was just a reminder of our horizontal antennas are typically navigation. Our vertical antennas are typically communications. So just kind of a reminder back to the polarization, which is back to our sideways antennas. Makes sense. Those are our navigation antennas. They're laying on their side. So antenna here laying on its side is going to communicate well with an antenna here laying on its side. Same thing for our, okay, I lied. Our glide slope one, yes, the same thing, but how do we pick it up extra special with that guy usually? It's a loop antenna, so. All right. Yeah, I thought the last one was bad. All right, test for security. All right, you're going to be my aircraft, two hands, because I'm checking to see if this is secure. When I'm checking my antennas, I don't want to knock this all the way over to Gavin. Bam! What I want to do is treat it like a guitar string and kind of. So, if Gavin was going to hold this thing securely onto the table, I don't want to knock it all the way to Micah and be like, "Oh, is this thing secure? I don't know. Is that a secure antenna?" What I want to do is go with it. So you can test antennas out there. You're after that soft little If it's not secure, you'll probably get a rattle, 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 and it'll stop, right? So what we're after is a nice gentle not a okay? Make sense? So you're not hitting them hard enough to knock it off the airplane. You're listening for versus okay? Simple enough. We're going to go test some at break here, which we're almost to. Prepware likes to say the best place for a VOR or a navigation antenna is on top of the cabin with the V facing forward. And then every airplane I check has the whisker ones back on the tail, or they're the plates with the holes that I pointed out, back on the tail. And I'm like, Prepware, where are you getting your info from? Because apparently Cessna, Beech, and Cirrus all disagree. But there's a Prepware question that says with the V facing forward, but the reality is most aircraft manufacturers put them on the tail. The V is still facing forward unless you're Dean, and then you switch them the other way if you used to be SMAT, because on a normal aircraft, if the V is facing forward, that's about eyeball height, like on a Cessna 150, you can poke your eyeball out. So it doesn't necessarily matter which way it's going, but they like to say V facing forward. Cirrus, not on the cabin, but these guys, this is what Prepware is saying. That navigation antenna, it's got the V facing forward, the antenna is right in the middle of the cabin. That is ugly as sin. So I'm pretty sure that's why nobody puts them on the cabin with the V facing forward. Is that ugly? Is that ugly? That is ugly. So I'm pretty sure that's why we disagree with Prepware is I'll go with a little bit not as good of antenna if it looks cool. That is one ugly antenna. But that's where they're after for on the cabin with the V facing forward. If I go back to my Cirrus, probably got a GPS antenna, little small guy. Probably got a nav antenna, right? So it's vertical. It's about the right length to be a nav antenna. And these other ones, I'm not sure exactly, but one of them's probably going to be my transponder system. So GPS with satellites, but also my transponders dealing with satellites and other stuff like that. So GPS is your positioning, where your transponder is the info coming back and forth from the satellites. This question they kind of like. Why do we seal an antenna? It's so we don't get corrosion under it. That'd be a bad day, right? Often these guys are ground plane antennas, so there's got to be a ground somewhere with the bolts. So usually we don't necessarily rely on the base to be grounded, but we're not putting sealant under there to insulate it. We're putting it around the edges so that water doesn't get underneath and corrode us. So that's a question they like is the sealant prevents moisture from entering. They'll try to ask you about, is it for pressurization? And it's not for pressurization. If it was pressurization, we would have to come up with some pretty heavy-duty fittings around this particular part for pressurization, right? We're going to worry about the small hole for pressurization. The sealant is to keep the moisture from getting underneath it. We use a lot of coax cable. 10x for bend radius is what we want to remember. Secure at least every 24. You can go to AC-43, 11-117. I'd recommend it if you get a chance. I was supposed to bring it in here. I got it. We'll do it really quick. AC-43, 11-117 says, we had this question the other day. It's going to be where it'll let me go down. What do you guys think it's going to be? Anybody? So, whoa, not on the screen. Minimum bend radius, any wire, they're going to say 10 times. But you get down to where you can be like, well, if it's breakouts, blah, 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 6, that's our normal wire. RF cables should not bend on a radius of less than 6 times the diameter of the cable. So basically, what they're saying is stick to the 10x, but if you want to push the envelope, you can go all the way to 6. You can go as tight as 6x. So most of the questions everywhere are going to say RF cables should be 10x, but if you want to push the envelope, you can go down to 6. So now if they have a question, what's the minimum bend radius for RF cables? Is it going to be 10 or is it going to be 6? And you'd be like, who's asking? If it was an oral or practical, you'd say it should be 10, but I can go to 6 if I absolutely have to. If it's a multiple choice question on a test, I would go with 10. That's how I'm going to put it. Because it all depends on who wrote the question. Sorry. Exactly, I just got a couple left here. Exactly the right length antenna. We already talked about basically more efficient and effective. This one in prepware is almost impossible because we have no idea what's going on the inside of that thing, right? It's a box. That could be a GPS. It could be just about anything. This one actually looks pretty similar to it. And I was going to pass it around the room. It's got a thing that says forward on it. I would say that's almost identical. Okay, so this one says loop antenna. That's interesting because prepware is going to call that one not a loop antenna. Sorry. This one is going to be ceiling mounted altitude encoder for a transponder. So if all they give you is this picture, oh, good luck. If it's mounted in the ceiling of your aircraft, the reason they mount it in the ceiling is there's probably a pressure tube that's going outside the aircraft. That pressure tube goes out to sense what the pressure is outside, and then it'll turn that pressure into an electrical signal to say to your transponder, I'm at 10,000 feet. So the trick on those ones, if they give you a picture, is if they say ceiling mounted, usually that means inside the aircraft, only the little poker thing is going through the ceiling. That's probably going to be an altitude encoder that works with my system. But if it's mounted under the aircraft, well, could be a loop antenna, could be a whole bunch of different stuff. So that is one last little trick. Usually they'll give you multiple electrical connections and a pressure. See the red on those? So the red on those is supposed to be giving you an idea that we're sensing air pressure. So it's our altitude encoder for our transponder, but I wish there was a better way. Canted antenna, already covered it. That's going to be a monopole, a whip, a Marconi, a quarter lambda. You get the idea. Usually we use these on our ELTs. That one, I couldn't come up with anything. I have no idea. I couldn't figure out what that is. I just take a wild guess. Depending on the size of it, maybe, GPS, it's going to be a higher frequency, right? But, I don't know. What was this from? This was our transponder antennas. Normally these guys, you look at the bottom of the aircraft, they're about this big. And you'll notice our transponder is one of our pretty high frequencies. So really high frequency, really short antenna. So that is typically our transponder. So when the radar beacon from ATC hits us, it's gonna both receive and send out the signal through that little guy that's about that big, hanging off the bottom of your aircraft. So short little guy, okay, what do I have that's a really high frequency? Pretty much you move up the line and go, well, it's probably not GPS because it's on the bottom of me. So we go, oh, it must be my transponder. Because we know our glide slope is a loop antenna, so that's not a loop. So coming down, radar altimeter, well, there's no pressure. It's on the bottom of my aircraft, so it's not GPS. Oh, probably transponder. DME is probably gonna be loop, so. All right, this one, go over when you get a chance, but here's our loop, here's our transponder, the short guy on the bottom, distant measuring, not gonna be blanked off by a wing, right? Marker beacons are, does it say the marker beacon on here? Bit longer, so it's actually a pretty good sized box. A lot of times they're under the tail. Our whiskers mounted horizontally are our cat's whiskers for nav. ADF sense is the long guy if we have one. ELT, well, where's our ELT supposed to be in our aircraft? Far aft as possible, so our ELT is always going to be one of the ones in here somewhere, right? So process of elimination, ELT, which is basically a comm antenna, right? It's going, I just died, or whatever. Our communications are typically going to be those verticals right above the cabin most often, and GPS. So it will be on the exam. I'm not sure which picture I have, but to locate which antenna is which. And once you realize I can do this by the length of them, I can do this by what they're looking at, I can get the ELT is going to be my empennage. It's a lot easier once you put all that info together. All right, this was the last one I added. Our last slide, null, our null static wick. And it wasn't until yesterday when somebody asked me that I actually understood why it's considered a null static wick. So I'm going to blank off this screen a minute. I'm going to draw my antenna. Now, an antenna works because I've got amperage going this way in this one, and that way in that one, right? What if I draw a static wick, and I give it two pokies coming out each way? If I've got current going out both sides, basically I have nulled any EMF coming off that thing, because whatever signal it would have been sending out got canceled by the other side. So I have nulled the effect of any EMF coming off my static wick by basically sending the current in opposite directions off each one of those little pokey guys. So when you look at these yellow guys, that's theoretically what they're doing there, is they're sending the current out opposite directions, each one of them. So the current going off them nulls each other. Now, there's a null plus. And the null plus one, I can't find any documentation on. It gets really tricky. But basically, the closest I can tell is if I've got a static wick, do I have one in here yet? I might have moved them all out. Here we go. If I've got a static wick that's flexible or semi-flexible, and it's going like this when I'm flying, there's never really a time that it's pointing at you, right? And we know with our antennas, if I'm pointing at Gavin with an antenna, is he going to get a signal? No. But if I start doing this, is he going to get a signal? A little bit, right? So our null plus, I think that one's a null plus, but basically, from what I can tell, they're a bit more rigid like that, so they're not flexible, and then they point backwards on the aircraft. So it doesn't necessarily have the two spikes to null each other out like an antenna, but if it was going to send a signal out, the signal's going to go up sideways from it, and if I go back to an aircraft, if I drew a signal with an antenna like that, basically all my comms are in that null area from this side, right? So the closest I can figure on the null plus is they're just paying really close attention that the static wick is pointing so that the null side of the tip of the static is away. Closest I can figure, bunch of research, nobody else can tell me other than a 70-year-old Navy document that's written with a questions, comments?